Yeah, good morning, guys, to everyone. Okay, the last class we discussed the problems in the second chapter, static load. Today we are going to discuss, few more problems, Then we move to the third topic today. Yeah, yeah. Therefore, are you able to see my PPT?
Yes, sir.
Yeah, these four problems, somewhat different problems we have discussed today, and a simple problem. This kind of problem you may expect in the any competitive exam, even gate questions also. Okay. So we discuss this problem, then we move to the next topic. Okay. We see the first problem. Yeah, pump lever rocking shaft is shown in figure. This figure, this figure. Okay. The pump lever exert the force of 25 Newton and 35 kilonewton concentrated at 150 mm and 200 mm from the left and right hand bearing respectively. See here they have the load where it is acting from the support of the shaft. The support is nothing but we are using the both and we are using the bearings. With the help of the bearings, the shaft will be rotates freely. And now they have mentioned that the load is acting 25 kilonewton, 150 mm from the right side of the support, and 35 kilonewton from the left side support. 200 mm from the left side support. Sorry, the left side support is 150 mm, right side support 35 kilonewton is acting from the support 200 mm in the right side support. The support is nothing but bearing. Okay. Now our aim is to find out the diameter of the central portion of the shaft, while the limited stress is given 100 megapascal. That is, now see here. We didn't discuss this kind of problems. Using the simply supported beam support concept and simple cantilever beam concept. We didn't, discuss in the earlier class. Now we discuss this problem and we move for the next problem, next topic. Now I take this. Just see the problem. Given data, 25 kilonewton, 30 kilonewton, 35 kilonewton, 150 mm, 200 mm, and the stress value is also given. Just keep in mind, and just I'm going to take this, this figure only. So this figure, I'm going to take my whiteboard. Oh, sorry. I can keep it here. You can try to solve this problem, because now I'm not going to explain more depth manner, but just we know that what is the reaction. Anyone try to find out and tell me the reaction. Right hand side support reaction A, RA, and the left hand side report reaction RB. See, RA is the left hand side and RB is the right hand side. What is the reaction force? Can you tell me that? Someone calculate and tell me that. Yeah, please. Now the given data we know already, right? Take some more support. I mean, sigma B is given 100 megapascal, right? Now, what is the reaction force RA and RB? Now, taking moment with respect to A for finding the reaction force at B. Okay, so now RB into 950, 150 plus 200, 350 plus 3 600, 950 is equal to, the load is given, left hand side load and right hand side loads are given, near the bearings are given, 25 kilonewton into 150 plus 35 kilonewton. They're given the load. Now what is the RB? Please someone tell that.
Sir, 31.58.
Yeah, thank you. Thank you. 31.55 kilonewton.
8 kilonewton.
Then similarly, can you tell me RA? Very simple, no? summation of the loads acting in the bar.
28.42.
28.42, sir.
Yes, thank you. 40 Newton. Now, what is the bending moment at C? I mean, we know that reaction force here, we know this load. Then bending moment at the left hand side bearing with respect to 25 kilonewton, we can say that, right? What is the bending moment? I mean, RA into at C, bending moment at C with respect to load 25 kilonewton and the support RA. But we are considering bending moment at C, then the 25 kilonewton may not be considered for finding the bending moment at C. Okay, bending moment at C is nothing but RA into 150. Can you tell me that what is bending moment? RA 4.26. I put all are in Newton millimeter. Okay. Then bending moment C, at bending moment D, tell me someone else. Bending moment D. Bending moment D. RB into 200.
6.30.
Thank you, Ba. So, I mean, this is a basic problem. You must be studied in the second year, but still, maybe some at least 30 to 40 students might be there. So, that's what I'm repeating this kind of problem and how we are considering this concept for our design analysis. That's what I'm repeating this problem. That's what I'm taking this problem. Okay. Now, I mean, now the bending moments, we have found the bending moment in C and D. Now, where the bending moment is maximum, that we are going to consider for finding the diameter of the shaft. Now, diameter of the shaft is given, I mean, not given. That's what our aim to find out, that the diameter of the shaft. What is the diameter of the shaft? Now, I mean, see here, bending stress is given 100 megapascal. Then find out this diameter of the shaft. We know, right? Bending moment is nothing but, bending moment is given. See, I mean, this bending stress is nothing but m by my by I. Then we can write it m by z in terms of m by z. Now sigma B is equal to my by I can write it m by z. What is z here? Pi by 32 section modulus, pi by 32 into d cube. I mean the y d cube. Then I mean this is bending moment, we know maximum bending moment we are going to consider for our design. Then we know that section modulus, I mean this is, from this we know that, I mean our limit stress, bending stress is, we know 100 megapascal. Okay. megapascal, you can sense it 100 Newton per mm square. Then this is, we know, 6.3 e power 6 divided by pi by 32 into d cube. Then you can find out the diameter of the shaft from this. I mean, diameter of the shaft from this, we can say that 86.3 mm. We can consider 90 mm. Okay. Now I come to the next problem.
Excuse me, sir.
Yes, I come to
Sir, in this question, like it was mentioned to find the diameter at the center of the shaft. So why specifically they have mentioned like we are not considering any scenario for the center?
See here, the shaft is assumed to be a uniform. You can find out the diameter of the shaft at the center because they have given the bending stress. They might be, they might have been found with respect to at the center of the portion. They are given the bending moment stress, bending stress. But
Okay, sir. Thank you.
we are not concentrating the bending stress and shearing stress. If we find that bending stress, later when the next semester you are going to study that, the same similar problem, we are going to put a pulley here and at what center, at offset from the center, how the bending stress and shearing stress. Corresponding that you are going to find out the equivalent bending stress, equivalent shearing stress. Based on that concept, you are going to find the limit, permissible limit. Then you are going to find out the diameter of the shaft. It's a very valid question. But now sigma b is given 100 megapascal. It may be suitable, particularly in the center of the shaft. It may be. Okay. So now we are not concentrating this. It's directly given. We are doing this. Now clear? Okay. Now I come to the another problem. Yeah, 1 minute. I can make it small size. Yes. Now the next problem is see here. The next problem, the axle 1 meter long is supported in bearing at ends, carry the flywheel weighing of 40 kilonewton at the center. Okay. If the stress bending is not exceed to 60 megapascal, the stress is given. And find the diameter of the axle. This is the overhang crankpin axle. This same problem. This is the 1 meter long supported bearings. This is a simply supported beam. Whatever we discussed earlier, it's like two loads are acting at the near the bearing. Now it's a simply supported beam. Exactly this simply supported beam problem. Just you can try to find it. I give you 2 minutes. Please, can you tell me this diameter of the rod? What is the condition here? What is the bending moment in the simply supported beam while the load is acting at the center of the beam? What is the bending moment? Deflection equation or bending moment equation?
Deflection equals to the
Yes.
Q by 48.
Deflection equation. Your voice is not audible.
Hello, sir.
Yes.
Yes, sir. Deflection equation is WL cube by 48 EI.
Yes. Now, bending moment. Now here they have given bending stress, right? So we have to find out bending stress. Yeah, the same problem I am going to extend in case 2. Whatever you are saying, that formula is applicable. Now, first we have to find out based on the bending stress, based on the limit, permissible limit of the bending stress, we have to find out the diameter of the shaft. Now, tell me that bending moment equation in simply supported beam. Maximum bending moment and while the load is acting at the center of the bar, center of the circular bar. WL by 4, right? WL by 4. Now try to find out. Yeah, try to find out the diameter of the shaft. I mean, we know that once you know W you know, L is given. Now sigma B is equal to earlier formula, same formula, M by Z. M by Z. Very simple. Please try to do that and tell me the diameter once you find it. I give you 2 minutes, 3 minutes. I give you that, because this kind of question you may expect in our I mean objective as well as any competitive exam also. See, GATE exam also, whatever they are preparing the questions, the students able to attend. They will not, they can't give extraordinary, complicated or very complicated questions they can't ask. Okay. What is the diameter? This is flywheel. This is bearing 1, bearing 2. At the flywheel, when the power transmission is going to happen, we are considering that 40 kilonewton. Now find out that, I mean, diameter of this shaft. Z equal to
Sir, around 94 to 95.
Can you verify it? I mean, I got it 119.3 mm.
Yes, sir. 190.
Okay, okay, sir.
Yeah, thank you. Now, the second case, now verify that the deflection of the shaft should not be exceeded. I mean, now we have found that diameter of the shaft. Well, fine. Now, the another restriction we not yet considered, right? While the transmitting the power, the whole arrangement should not deflect more than deflected to beyond the 0.36 mm. Then based on that, we have to verify our shaft diameter. Can you do that? We have to verify that our shaft diameter should not exceed. Meanwhile, the transmitting of the power, the shaft deflection should not exceed 0.36 mm deflection. Then whatever our shaft diameter is right or wrong. Please verify it. Then you already know that the formula deflection is equal to WLQ divided by 48 EI. Now you may consider material property E is equal to 200 GPa, 200 10 power 9 Newton per meter square. This is a material property. Now, whatever we have found, the diameter of the shaft is suitable or not, or we have to increase the diameters, quite little increase the diameter is necessary or not.
Sir, what was the diameter we got?
We got nearly 120 mm.
Okay, sir.
No, sir, it is not suitable. The deflection is coming with 0.41.
Yeah, 0.4 mm. Then our diameter should be bigger than the designed diameter based on stress, or should be less than that?
Sir, it should be greater.
Yeah, it should be greater. So we have to consider while designing the shaft, we should consider all the parameters, not only stress under the load. In the operating condition, also we should consider the shaft should not deflect beyond this 0.36 mm. Like that, we have to, based on operating condition also, we should consider the design criteria. Okay.
Excuse me, sir.
Yes.
Sir, how did we get the 0.36 mm value, sir?
That is no. I mean, that is someone told that 0.4 nmm. That is maximum
no, sir,
deflection. But the condition I'm giving, I have given the condition. The second
Okay.
is the shaft should not deflect 0.36 mm.
Yes, I got it. Understood.
Yeah, thank you.
Thank you.
Now come to the third problem. An overhang crank with a pin and shaft as shown in figure. This is somewhat a different problem. Crank and pin. Okay. So, I mean, the tangential load is 20 kilonewton acts on the crank pin. Determine the maximum principal stress and the maximum shear stress at the center of the crankshaft bearing. I mean, this is also a good problem. I mean, 20 kilonewton is acting at the tangential load. The remaining things are given in the figure. Please, I solve this problem. Please listen this. Okay, 1 minute. Yeah. See, the problem is given already 20 kilonewton. Please consider this is a 20 kilonewton. Now solve the problem. There are two cases. I am going to solve the problem at a 20 kilonewton cases. Okay. Now this is assumed to be 20 kilonewton. 20 kilonewton. Now we would like to find out the tau max and the sigma max. Okay. Now D is given. D is given here. I mean 80 mm. D is given. And I mean the offset distance from the axis of the crankshaft is given. I mean 145 mm. 145 mm. Right? That is, I can consider y direction. It's 140 mm. When the load is acting offset from the axis of the main shaft, where we are showing interest to find out the sigma max and tau max, then obviously even the problem may not given sigma max, tau max. Obviously the component subjected into shear as well as normal stress, because when this offset load is acting in the component, from based on the reference axis, obviously the component subjected to shear. Okay. I mean, here the x direction, the distance is given, the region of interest to load acting position is given, and x direction is 120 mm. Now find out the bending moment with respect to center of the crankshaft bending moment, right? Now Solution. Now bending moment with respect to center of the shaft. Now what is the bending moment? Now M is equal to W into 120. Then going to be 2.4 e power 6 Newton millimeter. Okay. Now, I mean, see, when the load is acting, this is going to be a bending moment with respect to horizontal axis. But a twisting moment also there in this torque transmitter based on the vertical axis, vertical distance, right? Then twisting moment, I mean, T is equal to again W into 140. It's going to be 2 e power 6 Newton millimeter. Okay. Now find out the bending stress with respect to bending moment. You know, right? M by IZ. Z is pi by 32 d cube. M is we know. Then find out that you are going to get 47.75 megapascal. And tau due to torque transmitted. Tau is nothing but, you know the formula, right? I mean 16T by pi d cube from the governing equation T by J is equal to G theta by L is equal to tau by R. From that relations, we can find out the shear stress 16T by d cube. Then from this, we are able to find out that shear stress 27.85 megapascal. Now, once we know that, we can find out sigma max. Sigma B by 2 plus 1 by 2 square root of the formula. Just sigma B squared plus 4 tau squared, right? From substitute this, you are going to get sigma max. Sigma max is 60 point. Someone find out the tau max. Okay. This is at this section.
So
Yes.
36.68.
Okay. Thank you. Okay. Now the last problem, then we move to next chapter today. The last problem, a rectangular strut is 150 mm wide and 120 mm thick. It carries a load of 200 kilonewton at an eccentricity of 110 mm. The load is acting, 200 kilonewton load is acting 10 mm offset distance from the axis of the rectangular strut. Okay. At 10 mm in a plane bisecting the thickness as shown in the figure. I mean, I draw the figure. Okay. It's simple. Also draw the maximum and minimum intensity of stresses with respect to the cross section of the strut. That's what our intention here. Here, I mean, this is clearly given. The load 200 kilonewton is acting offset from the axis of the strut. I mean, the offset distance is given 10 mm. I mean, even this kind of problem, you may not expect the figure, this problem. I mean, the second problem and the last problem, you may not expect even the first problem 1, problem 2, problem 4, you may not expect the drawing. Okay. So I have gone through some UPS service questions. They didn't give. Sometimes they didn't give the figure. You have to find based on the question. You have to understand and draw the figure. Okay. Now, I mean, they given the rectangular strut dimension load acting offset from the this. We'll see the problem. We'll discuss the problem now. Go to the next page. Now see here the strut given. I mean, most of the problem we discussed earlier, but this type of problem we didn't discuss. So that's what I selected these problems. But any problem you can easily solve if you are very strong in whatever we discussed, the basics. Now this is the axis of the strut. The load is acting, very simple problem. This is not a difficult one. The load is acting 10 mm offset distance from the axis of the strut, 200 kilonewton. Now find out the bending moment now. What is the bending moment? How much load is acting here? 200 kilonewton load is acting. The distance is now 10 mm. The distance is now 10 mm. Offset distance 10 mm. Can you tell me that stress, how much? What are the stress here now? On a compressive, I mean, this is side you may consider A, B, C, D. Now, we already know, right? What is the stress is acting in the direct stress? Compressive stress, right? Direct stress is compressive. I mean, the dimension is given. This is 150 mm. I mean that, this is 150 mm here. This is D is at 200, 120 mm. D is at 120 mm. Depth is 120 mm. This is 150 mm. I draw this top view. Okay, cross section 150, 120. Okay, now find out the stress component. Draw the stress component along the cross section of the bar. I mean strut. What are the stress component? Direct stress component. Direct stress. Direct stress is nothing but sigma c compressive stress. I mean 200 e power 3 divided by 150 into 120. Very simple problem. What is this stress? 11.11 megapascal. What is the bending stress here? Sigma B is equal to M by Z. Z is here. B, the concept BDQ by 12 divided by D by 2. That is Z. Then when you substitute that, M is nothing but P into E. P into E by Z. Then you are going to get sigma B is equal to 4.4 megapascal. Now, which one is more magnitude? The dominating stress is compressive only in the region AB, right? Now, this is a direct stress. Even CD side also, this is same stress, right? Now, what is the maximum stress here? 11.11 plus 4.4. I mean, the direct stress is greater than the bending stress. Direct is greater than the bending stress. And now find out the maximum stress and minimum stress. Then at this, at the side AB, at side CD. Okay. Now maximum stress at AB. 11.4 plus 11.11 plus 4.44. Then it will be 15.55 megapascal. Minimum stress in the side of CD. Okay, now we would like to draw the stress distribution diagram here. Stress distribution diagram, with respect to this cross section, we can draw it now. This is axis. This side is .67 megapascal. This side is 15.5 megapascal. Okay. Now I stop it here, and I would like to clarify one doubt. Last class someone asked a very nice doubt. So there is small variations, small discussion. We do it, then we go for the next chapter. So I tell you that there is small mistake. I did it in the last class. We correct it now. Okay. Now see here. I mean, guys, please carefully see this problem. I mean, here there are two loads. I mean, they have given the resultant, okay, resultant force 6,000 Newton, right? The resultant force can be resolved into two components. One is vertical component and horizontal component. The problem is here they have given 45-degree angle. When the load is acting 45-degree angle, any load acting 45-degree angle, then the horizontal component and vertical component both are in same magnitude, right? But our intention, our aim was in the last class. Okay, I'm not able to. Okay, first remove this. Just give me a minute. Yeah. Now the horizontal load PH and vertical load PV both are same magnitude because of the resultant load is acting 45-degree angle. Cos 45 and sin 45 both will be same load. Okay. Now our region of interest here, the region of interest is here. Hence, this cross section going to be subjected into direct tensile with the help of the pH. The pH effect going to be here. Due to pH effect, sorry. The pH here, direct tensile. Now, the PV going to be a pure bending. The PV is going to be generating bending moment, not pure bending, sorry. The PV is a bending effect, right? The PV is bending effect. The PV doesn't create any tensile load on, tensile along with respect to the cross section. The PV is there with the help of the PV able to find out the bending moment of the component in this cross section. Okay, hence the one small mistake has been done in this problem. Here that the direct stress is a vertical component. It's not vertical component. It should be a pH by A. pH by A. That's all. Remaining things are same. This is direct load. pH by A. Now this is the, this is a pH. pH also same magnitude because of 45 Okay. Now you can find it out. The bending moment going to be PV into 130 because in this case the bending moment will be considered with respect to vertical load and horizontal distance. Vertical load and horizontal distance. Okay. Suppose if I'm taking the this cross section, here, I would like to find out the stress component in this region of interest. Then during that time, the PV is going to be a direct compressive. In this case, sigma tensile will be based on sigma tensile will be found with respect to pH. But in this case, the sigma C will be found out with the help of PV. But in this case, the bending moment with the help of going to be with the help of PV. In this case, the bending moment in this region with the help of pH into 75. Okay. Now this is the subjected into compressive stress. Suppose if I am taking the cross section here, during that time, this section if I'm taking the cross section Z, then during that time pH and PV both are playing important role. Both are playing the important role. So that's what last time I didn't clearly tell this information. Appropriate information I have told the last time I told that. Please correct it. If you have any doubt, please now you can ask me that. Okay? Are you clear? Someone asked this doubt. Who asked that? I forgot his name.
Sir, he was a
Bilas. Yeah, Bilas. Now are you clear?
Yeah, yes.
Okay, now we move to the third chapter. Third chapter. Now we are going to third chapter. Yeah, guys, I'm giving you some few minutes. If you have any doubt, please ask me in the last chapter. If you have any doubt, please ask me that. Okay. Now, design against fluctuating loading. I mean, whatever we discussed in the earlier case, static loading, the components also it's uniform cross section like that we discussed. Now I'm going to ask you in this chapter beginning. Now I'm asking one questions. What are the given below equations? Is it suitable in the right side figure or it's right side given components? The equation, is it suitable or not? Yeah, please reflect your answer. If you say the suitable, why it is, how it is suitable? If you are not saying not suitable, if you are saying not, then what is the reason behind of it? Yeah, very simple question.
Sir, I don't think they are applicable, sir, because the cross section is not uniform.
I mean, see here, you are correct. Now you are correct in that sense. You are missing some information. This is cross section is uniform.
Sorry, stress applied is not uniform.
No, that also uniform. See there's that stress magnitude also showing the direction, that also uniform.
Okay, you're talking about first.
Still one more. Its answer is there within the figure itself.
Sir, due to the hole present in
Yeah,
between.
exactly. You might have been done the experiment in the second year, that universal testing machine, in the tensile test, normal tensile test in the standard test specimen. Have you designed any holes in the specimen while conducting the experiment? No, right?
No, sir.
Yeah.
Around the hole, the stress will not transmit uniformly.
Yes, because I mean, as per the standard test specimen, whatever we considered that the standard test specimen concept when we studied theories of failure, there are 5 theories of failure. I mean, 5 failure theory we discussed: maximum normal stress, maximum shear stress theory, energy distortion, distortion energy theory, maximum shear stress, shear strain theory, right? All the theories, we assumed that the standard test specimen, but the standard test specimen, we never used holes inside in the design. We assumed that the uniform cross section without any discontinuity. This is like a discontinuity. Okay, hence when the component discontinuity is presented, these equations we can't use that directly. We can't use these equations. I mean, this is what when the component is standard test specimen, subjected into compression or tension, we are using this formula. But when the discontinuity is presented here, we get it very difficult to use this formula. Similarly, when the component in bending behavior, when the component in torsion behavior, during that time also, this such a kind of the holes are presented, we can't use this formula directly. Okay, so we discussed the briefly we discuss the reason, then we go for the next thing. So here, I mean, the cross section of the component doesn't has any discontinuities when we are using this formula. When you are using this formula, the component doesn't has any discontinuity. No discontinuity. No discontinuity. This formula applicable. Okay. Now, but one thing, but we cannot always use this kind of components, right? We cannot always use this kind of components, a very exactly plain component without holes. We can't use. We need holes whenever required. For example, to connect, I mean, any mechanical system means it will be connected more than two components, right? When we are joining these two components, we need holes. Either holes can be used for riveted joint, either holes can be used for joining this two component with the help of the bolt and nuts, right? Hence, we need the holes. The holes, it should be presented when we are going to connect the two components to functioning the mechanical system, functioning as a mechanical system. Hence, we can't always use this kind of components. The another, I tell you the point by point, because we need to have the holes, keyways, oil holes, grooves and spleens, etc. Right? Such a kind of design is required based on our machine operating condition, as well as fabricating our component with each other. The fabricating component with each other with the help of the bolt, nut, or pins, or welding, right? And it may be a screwed joint. Okay, then we need a holes. We can't use a plain component in our system design. Okay, we need this kind of arrangements also. Okay, then hence in practical conditions we cannot avoid this type of discontinuities. The discontinuities we can say like this: holes, keyways, or screwed, holes, keyways, grooves, or threaded portion. We can't avoid that. These are called discontinuities while preparing the designing the component. We can't avoid this kind of design while preparing our component. But one thing, when the hole is presented, then how the people gone through that, some kind of studies. Or if suppose this looks like a discontinuity, when the discontinuity presented, either the stress is getting varied or else it will be same like that. The people gone through research and they verified and proved it. When the discontinuity presented, that region more stress concentration. See example, this is the simple example. Whatever we thought in the theories of failure, we are always considered in the right hand side of the theories of failure for maximum normal stress theory is equal to sigma 1 is equal to, we consider the greater than or equal to means it will not be a failure, right? When this normal, sigma 1 greater than or equal to the stress, sigma 1 is greater than or equal to the stress value obtained from the normal tension test, sigma, right? We assumed that. But when the discontinuities are presented, then we have to introduce here also safe factor. That is nothing but a stress concentration factor for design the component in safe design, in safer side. Hence, people gone through the studies with the help of the, photoelastic technique. In the photoelastic technique, especially they used the polariscope technique. What they did, they have prepared the sample with epoxy resin. Then they kept below the polariscope and they applied the load here. Now the epoxy resin sample is with the hole they prepared. Then they performed the experiment now. They performed the experiment in that sense, they applied the tensile load in the both sides. They applied the tensile load in the both sides. It's a uniform cross section here. Then they applied the tensile load in the both sides. Then finally they came to know that in the polariscope report says that the stress magnitude is greater as compared to the uniform cross section load is acting, which side is which load is acting at the uniform cross section of the specimen. Then finally, that with the help of the photoelasticity concept, we observed that we have understood that the magnitude of the stress is, that sudden rise in the magnitude of stress in the vicinity of the hole. See here, the cut section they have clearly explained here. The vicinity of the hole, that the stress concentration is more. The magnitude of the stress is more as compared to the uniform cross-section stress. But this stress is obtained our elementary equations, sigma t is equal to P by A. Right? Hence, then we can come to the conclusion the stress concentration is defined that localization of high stress, this one. Localization of high stress here, localization of high stress due to the discontinuities present in the component, and also we can consider when the component change in shape, abrupt changes in shape, also creating the more stress as compared to the normal standard test specimen, as compared to the stress obtained from the normal standard test. Okay, so now we can come to the conclusion the stress concentration factor is now, I think this is already I explained this. Already I have explained this. Now the stress concentration factor is nothing but sigma max by sigma mean. The sigma max is the developed stress at the vicinity of the hole, but sigma naught is stress obtained from the nominal stress. This is the nominal stress obtained by this elementary equations P by A at minimum cross section. This is nothing but we obtain the stress from the normal standard test specimen, the sigma naught, but sigma max is at the vicinity of the discontinuities present in the component. Then similarly tau max, shear stress also, this is nothing but our stress concentration factor KT, stress concentration factor. Now this is the things already we discussed, just we go through that. I read this points. In practice, the discontinuous or abrupt changes in cross section, any missed point I will tell you that. Most of the things I told already. Okay, now see that just the stress concentration is defined, that localization very important. You can expect this kind of questions in your interview also. Okay, the stress concentration factor is defined as the localization of high stress due to the discontinuities or irregularities present in the component, and also when the component change in the cross section. For example, the shaft may be change in cross section, stepped shaft. This is a more stress concentration. These regions are going to be a more stress concentration. That's what we are saying. Abrupt change in cross section of the shaft. So this is a stress concentration formula. Please keep in mind this entire things we very important formula. Now, what are the reasons? The magnitude of stress concentration factor based on this some reasons. What are the reasons? Whatever we discussed, KT is now theoretical stress concentration factor. The T denotes the theoretical stress concentration factor here, KT. Now see here, what are the reasons? What are the parameters should be considered for the stress concentration factors? Variation in material properties. See here, in practical, actually in theoretical condition, we are assumed that the material is homogeneity. Theoretical conditions, because we are doing a number of simulations using CA softwares, either Abacus or ANSYS or COMSOL, and there are so many softwares. We are using that software and we are defining the material properties. During that time, we are defining the material properties like homogeneous material properties. But in practical conditions, we cannot expect that. There are so many factors. For example, internal cracks or flaws may be created while in the material in the functioning. Also cavity or weld. I mean, cavity is present while welding, because as I told you that when we are connecting two components, we are going for the welding or bolted or bolt or nut joints or screw joints like that. When we are welding, then it may be a possible of cavities. Air holes or porosity may be presented when we are casting the component. That also, I mean, the presented in the porosity or air holes, air bubbles or porosity formed inside the component, then that will be acting as a stress concentration. So these are the parameters we should consider. That's what people are going for, while that once they prepared the material for particular component, then they're going for non-destructive testing concept. I mean, non-destructive testing concept, we are able to see the signal behavior. Based on the signal behavior, we can realize it, what is there inside the material. And people are going for X-rays. People are going for computer tomography. I mean, you may not studied these things. Just to keep in mind, computer tomography is nothing but we can analyze the material layer by layer. Any porosity or blowholes or composition changes are happening that can be easily detected with the help of the computer tomography. That is a three-dimensional X-ray. It's nothing but three-dimensional X-ray. We can see that component internal structures layer by layer. Any porosity presented or air bubbles presented, it can be seen with the different images. If based on the image, we can come to the conclusion the material is good or not. Then we can modify it later based on our application. Now I come to the load application. I mean, see, when the components are mechanical components or mechanical system is functioning, they are not only subjected into tensile or compressive or bending or torsion. It may be combined all together, maybe the combination of tensile and bending, or maybe the combination of torsion and bending. I mean, that's what the machine component subjected force at either point, but whatever forces, whatever stresses are acting, it may be in the point or overall small area also. It may be in the point or small area also. Whatever the force component I told you, that the shear or tensile or compressive or torsion or bending, it may be acting in the small area or it may be acting in the whole area of the component. When the small area is acting, then it will be a problem, because that area going to be a more stress. I mean, it may be exceed the limit, permissible limit of the stress, either compressive or tensile, whatever, or even shear also. Okay. For example, I can tell that example. We discussed already. I mean, the gears, pinion and the gear, right? The pinion and gear, there are for example, in pinion 20 teeth, 20 tooth is available, 20 tooth are available, but in gear maybe 40 tooth are available, but all 40 tooth not contact at a time. Any one of the teeth from the pinion, any one of the teeth from the gear going to be messing together, messing for transmitting the power in fraction of second. Then another teeth will come and engage with the pinion. I mean, so I told you, this is the pinion. Just to give me a second, I draw it. This is, for example, this is one teeth. For at a time, one teeth only going to be engaging the transmitting of the transmitting the power. The remaining teeth are going to be ideal, right? While messing these teeth, it may be a line contact or point contact. Line contact, mostly line contact, or point, mostly line contact. Then when the line contact, very small area, then the stress concentration will be more in this region of interest, right? For example, another example, cam and follower mechanism. It's a line point contact. When the point contact, it will be a more stress concentration because the very small area, infinitesimal area. Similarly, we can consider this ball bearing. The ball bearing, while you can see that the bearing you can see easily anywhere in the mechanical component. Even you can see that in the easily all the other components also. Then they are also more stress constant because of the point contact. Another example for rail and wheel, it's a line contact or point contact. Then more stress concentration. Then while designing these components, we have to consider the stress concentration factors, but before designing the component. That may be a step with respect to static load as well as fluctuating loads. Okay. Now I come to the abrupt changes in section. I mean, as I told you that, I mean, for example, now I take simple shaft. The shaft is connected to, for transmitting the power. The shaft is connected to the motor. The shaft both end will be connected to the bearings. The shaft will be connected with the pulleys, right? When the shaft connected to the bearing, the shaft going to be changing the cross section. We are making, stepped shaft. Then we are connecting the bearings, right? Then the change in section, change in cross section, change in shape of the shaft also going to be more stress concentration, especially these regions. Okay. Similarly, now the last thing, I mean, discontinuities of the component. What is the discontinuity here? I mean, when I'm connect, this is, for example, the same shaft, I tell you this two end is connected with the help of the bearing for free rotation, right? Now the shaft is going to be connected to the flange or hub for transmitting the power. When the shaft is connected to the flange or flywheel, then we need some keyways here. Then this is called discontinuities. Either keyways or holes or bolt and nut concept or keyways, right? Or pin and cotter we may use to connect this securely to connect the flywheel. Hence, we need to provide the discontinuities in the shaft that may cause us the stress concentration. So these are the parameters we have to consider while for the designing the shaft. And this machining scratches or surface cracks and macro cracks or micro cracks also people, I mean, proved it's going to be a failure because of this stress concentration, because of the cracks. The cracks also going to have soft corners. I mean, but it will take long duration. After it will be failure. So suppose the crack size is micro, then it will take a long duration. The shaft is going to be failure. Suppose the crack is macro cracks, then that it will be failure as soon as possible. So these are the things we are going to discuss in this chapter, and this is the already explained. No, now see here one small video how the cracks is playing in this stress concentration. Just I show you that. Are you able to see this video?
Into the typical
I stop here.
Failure of a reinforced
Hey guys, someone reflect. Are you able to see this video?
Yes, sir.
Yeah.
beam. The beam is simply supported over the span of 3 meters.
Yeah. Before apply the load, are you able to see here? If there are few cracks in the beam. The beam is simply supported beam. They apply the load with the help of the vertical arm. I mean, see here the arrangement, vertical ram. Okay, are you able to see here small cracks are there?
Yes, sir.
Yeah.
Yes, sir.
See, when they apply the load, the failure going to first initiated from this cracks only. And wherever the good region, it will not be affected easily. But where the cracks is initiated, there only crack is already present. It looks like micro cracks. As compared to the same dimension of the shaft, dimension of the bar, the cracks are very, very small as compared to dimension of the bar. But when the load is acting on the beam, simply supported beam, the first thing, this is the crack is the main guy for initiating the failure. Just see that.
It is subjected to
Beautifully they prepared with the test, experimental things.
The load is applied through the hydraulic cylinder. The load cell records the load.
This is called load cell. Okay.
LVDT measures the mid-span deflection in the beam. There are 2 strain gauges attached to the beam. The first one is at the top concrete surface to measure the compressive strain in the concrete, in the top fiber. And the second one is attached to the steel in tension to measure the tensile strain in the steel. All the data is fed into the data logger. The cross-section of the beam we are testing is as shown here. The width is 150 millimeter and the depth is 250 millimeter. It is reinforced with 2 N12 bars. N stands for normal ductile 12 millimeter bars. Let's have a look at the loading.
Yeah, see here, before loading, see here, these are the looks like some lines. Looks like somebody make like lines with the help of the pencil. You may think like that, but this is very small cracks as compared to dimension of the beam. It looks like we scratched with the help of the pencil. We drawn a line with the help of the pencil like that. But when apply the load, you see that the failure is going to start from the cracks. Now they are going to insert the load, see here.
As we can see, large vertical cracks are appearing in the maximum moment region. We can also see a large deflection happening in the beam. The cracks are widening, and finally the concrete crosses in compression, and that's where the beam fails.
See? So are you able to see now? Are you able to see this crack?
Yes, sir.
Yes, sir.
Yeah. It was earlier looks like a line, something we are scratched with the help of knife, or we might have been drawn like lines, but it looks like surface cracks. But the surface cracks also very important parameter for the failure.
This is a typical flexural tension failure mode where the tension steel yields before the concrete crosses, and also it is characterized by large vertical cracks and a large deflection as well. If we look into the moment versus mid-span deflection for this beam, we see a very ductile behavior. Initially, the beam is by this large yield plateau, 0.0022, the crushing of the rise by a large yield in the crushes, and it is a very ductile failure mode.
Okay, I will share you the link. You go through that. Okay, the last one. Yes. I mean, that is another one of how the stress concentration factor. You see this simulation. I thought to show, yeah. See here, when the abrupt change in shape of the component. I mean, we are using the car bodies, car structures. It's not a uniform cross section, right? When the car is subjected into crash load, I mean impact load, what will happen? See here, this is the change in shape of the structure while the load is acting on the frame. How the stress amplitude change with respect to change in the amplitude, magnitude or changes, magnitude or increase the stress amplitude. See here the figure. See here, these corners, are you able to see the corners? The corners are going to have a more load, more stress, because this is because of the corners. This is subjected to maximum stress, right? But the people, I mean, automobile industry is very important. The crash analysis is very, very, very important in the automobile industries. I mean, they are based on this design, but while the inside, what is our primary aim here? I mean, who are the sitting? The driver shouldn't affect when the car is crashing, right? Then before this high impact says reach, you should not reach to the driver, inside the driver. That is their ultimate aim. I mean, how to observe? Before reaching to the driver, the stress should be observed with the help of this component, with the help of this structure. That's what they are doing, a lot of crash analysis stress, and based on that, they are defining this component. But there are one thing, the material is also failure, but also we have to shave the human beings, I mean, driver also we have to shave. Then based on that, we are defining this material design as well as this structural design as well as they're defining the material. Okay, I will share you this video also. I have another 2-3 videos we will see in the next class. I mean, as of now, whatever we discussed, corresponding videos I showed here. I mean, the last thing today, the stress concentration factors defined. There are 2 methods. One is mathematical model based on the theory of elasticity, and the experimental methods. I mean, using like a photoelastic concept. But we cannot go always experimental method, because I mean, we have to prepare the non-uniform geometry of the component structure, and we have to apply appropriate load and at a particular boundary condition. Then we have to study. It's a very difficult job, but it more time consuming process, and the cost, it will be a more costing, right? Then we would like to avoid that. Now people are always behind of FEA software, because once you complete your design with the help of the CAD software, then you can go for the post-processing and pre-processing, post-processing and visualization. Then you can easily apply the load condition. You can easily define your boundary conditions at the different boundary conditions. At the different boundary conditions, you can define your different load conditions. That can be done very easily and very fast manner and cost-effective method. Then, but FEM will not give you 100% truth result, but this is approximation. Then we can easily understand the stress concentration, where it is more, where it is less, like that, as I shown you the video from this. Okay.
Excuse me.
We'll stop here. The next class we will discuss remaining things. See here that the corner surface are maximum stress concentration. Okay, stop here. Yeah, guys, if you have any doubt, please go ahead. Yeah, any doubts? Yeah, when will start our midsem exam?
In first week of October, sir.
Okay. Sure, we can complete third chapter as well as fourth chapter also. But anyway, we are in appropriate speed. Yeah, guys, do you have any doubts?
No, sir.
Okay, thank you. Pawan, are you there in the meeting? Thank you, Pawan. Shall I close the meeting, Pawan?
Yes, sir.
Okay, guys. Have a nice day. We'll see you in the next class.